Welcome. In this video, I'm going to show you how to find the volume of a solid of revolution using cylindrical shells. The region is bounded by y equals x squared minus x cubed in the x-axis, and we're rotating about the y-axis. If you're part of my calculus course, you were asked to graph at least the two-dimensional version in the module as a warm-up activity and then use that to sketch a three-dimensional version in your own notes. I'm going to show you how to use technology to sketch both a two-dimensional and a three-dimensional version. So the first thing we're going to do is type in f of x equals x squared minus x cubed. There. And now I really want to limit this to just x values between 0 and 1. So I'm going to quickly rewrite this as capital F of x equals, and now we need to use some if statements. So if x is greater than 0, that means x value is bigger than this point, comma, and then another if statement. If x is less than 1, so less than this number, comma, and then I can write just little f, and suddenly I have just the part I want here. This is x squared minus x cubed on top and the x-axis below. Now you're going to want to go to the bars here and go to View and click on 3D Graphics and then close that out. And then for easy viewing, I'm going to take off this gray box. There we are. And now here, you're going to input surface, and then we're going to type in f of x. We're going to type in 2 pi, and we're going to type in y-axis. And as you can see here, we have a three-dimensional graph, but it's kind of tricky to see what's going on. And the real art comes from being able to move this around really neatly. So this is what we see in the two-dimensional plane. The red line is the x-axis, the green line is the y-axis. Let's zoom in a bit. And I'm just zooming in with my mouse here. And now I'm going to move my cursor on the green axis and pull this up. And then I need to move the graphics view a little bit more. Okay, so after a little bit of manipulation, I got a picture I'm happy with. As you can see, here's x squared minus x cubed, and it's cut off at the bottom by the x-axis, and that's again here in blue. And then our shape looks, I don't know, I would describe it like a bundt cake almost, a bundt cake that doesn't have the full hole in the bottom. And if you want to make the shape a little clearer, you can go to settings here and go to color. There we are. And I'm going to make it more transparent. There. And I'm happy with that. Now I can really see what's going on with this shape. All right, now that we have a good idea of what this looks like, let's go back to figure out what the volume of this shape is. So as you can see here, I have a graph of f of x equals y. That's this function here, bounded below by the x-axis. And you can see it here in our three-dimensional sketch and its mirror image, along with the solid that it makes when it's revolved. And again, that's about the y-axis. So now let's review what exactly it is we're doing with cylindrical shells. So here's a sketch of a representative cylindrical shell. As you can see, this height here is f of x. And this thickness of the actual shell goes along the x-axis, so that's the change in x. That's delta x. Imagine I've rolled it out here. So there's my rolled out cylinder. That is, I cut it kind of like here and then flattened it out. Well, this height here is still f of x. And this thickness here is still delta x. We're missing one thing. That is, what is this distance here? Well, this distance is precisely the circumference of the circle in green up here that is the base of this cylinder. And how do you compute circumference? Circumference is equal to 2 pi r. And in this case, what's r equal to? Well, our center of our cylinder is here, and the radius goes out in this direction, so r is actually equal to x. So that is the circumference is equal to 2 pi r, but since r is equal to x, we have 2 pi x. And now, in order to find the volume of this rectangular prism here, and again, this was formed by taking this cylinder, kind of slicing it along a side, and then just imagine rolling it out. We have to multiply this length here times this height times this thickness. So the volume of this one cylinder is given by f of x times 2 pi x times delta x. And that's the volume of one cylinder. So clearly then, the volume of the solid, since we want to add up an infinite number of volumes of these cylinders, is the 2 pi times the integral of f of x times x dx. And now what are our limits of integration? X runs from a min of 0 to a max of 1. All right, so now we can replace big f of x with x squared minus x cubed. So we end up with 2 pi times the integral from 0 to 1 of x cubed minus x to the 4th dx, which integrates really nicely. And you end up with 2 pi times 1/4 minus 1/5. So this is just 2 pi over 20, or pi over 10. So then the volume of this region here, the volume of this solid created by rotating this region about the y-axis is pi over 10. I hope this video was helpful.